In this video, we're going to talk about electrochemistry. So electrochemistry is an area of chemistry where we look at the conversion of chemical energy to electrical energy and vice versa. So we're looking at the transfer of electrons and how we can use chemical energy to make electrical energy, or go in the opposite direction and turn electrical energy into chemical energy. So in electrochemistry, we're often concerned with different types of cells and the reactions that happen in those. Two that we're specifically going to talk about are the galvanic cell and the electrolytic cell. So the galvanic cell is also called a voltaic cell. It's a type of cell in which we have a spontaneous chemical reaction. So the key word here is spontaneous. This isn't something that we're forcing to happen. It occurs on its own. A spontaneous chemical reaction which generates an electrical current. And we can use that electrical current to do various things. So for example, the batteries that are in things like your calculator and your cell phone are galvanic cells. So that chemical reaction generates an electrical current, which you use to do various things with. The electrolytic cell is the opposite of a galvanic cell. So an electrolytic cell is a reaction in which an electric current drives a non-spontaneous reaction. So we use an electric current to convert electrical energy into chemical energy. So let's take a look at some galvanic cells here. So we've talked about redox reactions in the past. So if we look at this reaction, we can see that zinc goes from being neutral to being 2 positive, which would be an oxidation reaction. And copper goes from 2 positive to neutral, which means it gained electrons, so that would be a reduction reaction. So we can separate out our oxidation and our reduction half reactions. We can write the element that gets oxidized by itself, and we write the electrons that are transferred. Since the electrons are lost, this is an oxidation reaction. The electrons are products. In a reduction half reaction, this time we have copper 2 positive turning into copper metal. So we gain 2 electrons. We're adding 2 electrons to our copper that has a 2 positive charge. So the 2 electrons are reactants. If we add these reactions together, we would get the reaction at the top. So if we actually had this in solution, so here's our zinc metal here, and we have a copper sulfate solution here. So we have copper ions floating around in solution and sulfate ions floating around in solution. Now we don't really care about the sulfate. It doesn't affect the reaction in any way. What we care about is the copper. So if we looked at this on a microscopic scale, so we have our little zinc ions here. So the zinc atoms that are on the surface of this come into contact with copper ions in solution, and what happens is occasionally some of these copper ions transfer some electrons. So it's actually the zinc transferring electrons here. So zinc transfers 2 electrons to copper. So copper accepts those electrons and becomes neutral. So we get some copper metal here. And then zinc floats off into solution. Zinc is now a 2 positive ion. So it floats off into solution. And this keeps on happening. Then we actually get an area here on the surface where we have copper metal plating the surface of our metal, and then we have some of that zinc that's floated out into solution. So if you look at the top picture here, if you look at this top picture, you can see that our metal is just a nice silvery metal. And if you look at our metal down on the bottom here, you can see a darker color on the bottom of this metal that's been in solution. That's where the copper has actually pleated this metal zinc that we had. So you get a dark copper color on there. So if we look at our reaction here, if we add these two reactions together, you'll notice we get zinc metal plus copper 2 positive in solution gives us zinc 2 positive in solution plus copper metal. So if you look at the half reactions, that we have two electrons on the product side here, and we have 2 electrons on the reactant side of the other reaction. So those cancel each other out, and we're left with our overall cell reaction when we add these together. So the overall cell reaction should never contain electrons. Okay, so make sure when you're adding together an oxidation reaction and a reduction reaction that you cancel out your electrons, because the overall cell reaction should not have electrons in it. Okay, so if we look back at our oxidation and our reduction reactions, so when we have an electrochemical cell, we have 2 parts to it. The 2 parts that we have are an anode and a cathode. So an anode is the half of an electrical cell where oxidation occurs. And the cathode is the part of the cell, the part of our electrochemical cell, where reduction occurs. So if you like little mnemonics and word associations, one way that you can use to help you remember the parts of a cell is that anode begins with a vowel and oxidation begins with a vowel. So the 2 vowels, anode is where oxidation occurs. Cathode begins with a consonant and reduction begins with a consonant. So cathode is where reduction occurs. So if we look back at our half, so if we look back at our 2 half reactions here, the anode is our zinc part of our cell, and the cathode is our copper part of our cell, where reduction occurs. So we can actually write those in a shorter notation. What we do is we write the shorthand notation here. So the first part of this is the anode, where our oxidation occurs. And the second part of this, beyond the double lines, on the right side of the double lines here, is our cathode, where reduction occurs. So we start with the solid metal, and then we show the charged species in solution. So we put a single line between those. That half on this side, on the left side here, is our anode for our cell. And then we have a double line. And then we put our ion in solution and our solid metal with a single line between them for the cathode, where reduction occurs. So what this double line represents is a salt bridge. So if you think about these two, if we had an electrochemical cell, and you might have seen these little diagrams in a science course in the past. So we have our two cells, so we have our zinc in solution over here with our piece of metal. And then we have our copper in solution with our piece of metal. So these two aren't magically by themselves going to jump over into each other. The copper's not going to magically jump over here to the zinc, and the zinc's not going to magically jump over to the copper. We have to have something connecting the two. So what we have connecting the two is a salt bridge. So we would have a bridge here that connects the two of these, that allows electrons to travel between these two cells. So this here would be our salt bridge that is allowing the electrons to travel between our zinc anode and our copper cathode. So these double lines represent the salt bridge. The single lines just separate the metal from the solution. So the first half of this is our anode half cell, and then on the right of the salt bridge is our cathode half cell. And the single line represents a phase boundary between the solid and the aqueous part of our half cell. And then we have another phase boundary on the cathode side. So electrons flow from the anode, which loses electrons, to the cathode, which gains electrons. So the force or electrical potential that pushes those electrons away from the anode and pulls them towards the cathode is called the electromotive force. So sometimes we also call that the cell potential or the cell voltage. So you hear the term cell potential and cell voltage quite frequently. We don't use the term electromotive force quite as often, but it is technically the name for it. So we measure cell potential in terms of energy, and the SI unit of energy is the joule. So the joule is actually made up of a couple of other different units. So we define the joule in the first part of the semester as kilograms per meter squared times second squared, which is the technical definition of it. But we can also break a joule down into a coulomb times a volt. So 1 coulomb is the amount of charge that is transferred when we have a current of 1 ampere flowing for 1 second. So an ampere is the unit for current. So if we have 1 ampere flowing for 1 second, we have a coulomb. So that's our unit for electrical charge. And the SI unit for electrical potential is volts. So if we multiply Coulomb times a volt, we have a joule. So we can use those units in a lot of different ways. So one of the reactions that we're going to look at, or one of the equations that we're going to look at, is how to calculate free energy change in relation to electrochemistry. So if we have our free energy change, or we're trying to calculate our free energy change, that's equal to the number of moles of electrons that are transferred in the reaction times the Faraday constant. So the Faraday constant, as the name implies, is a constant. It's the electrical charge on 1 mole of electrons. And it has a value of 96,500 coulombs per mole of electrons. So you don't need to memorize the equation or the value. You'll be given those. You just need to memorize them. So delta G is equal to the negative of the number of moles of electrons times the Faraday constant times the cell potential. Or, if we have things under standard condition, which is 25 degrees Celsius and 1 atm, then delta G naught is equal to the negative of the number of moles of electrons times the Faraday constant times the standard cell potential. So let's take a look at an example here. The standard cell potential at 25 degrees Celsius is 1.10 volts for the reaction zinc plus copper 2 positive gives us zinc 2 positive plus copper. And we want to calculate the standard free energy change for this reaction at 25 degrees Celsius. So we were told on the last slide that delta G naught is equal to the negative of the number of moles of electrons times the Faraday constant times the cell potential, the standard cell potential. So we know from looking at the half reactions that the number of moles of electrons that is transferred is 2. So we can take the number of moles of electrons, which is 2, and let's go ahead and write that out. So 2 moles of electrons times the Faraday constant, which is 96,500 coulombs per mole of electrons, times 1.10 volts. Now we already have a little problem here because moles of electrons cancels with moles of electrons, but we're left with coulombs times volts, which doesn't do anything for us. So we know that 1 joule is equal to 1 coulomb times 1 volt. So we can add a conversion factor here. 1 joule over 1 coulomb times 1 volt. That gets rid of coulombs times volts. So coulombs cancels with coulombs and volts cancels with volts, and leaves us with joules, which is the unit we would typically use for delta G. And we actually want to go ahead and convert this to kilojoules, so I'm going to go ahead and add a 1,000 joules per 1 kilojoule, so that I can go ahead and get delta G in kilojoules, which is the more standard unit. So these two conversion factors here at the end get me out of coulomb times volts and changes us to joules, which I can then convert to kilojoules as a more standard unit for delta G. So if I take negative 2 times 96,500 times 1.1 and divide that by 1,000, you should come up with negative 212 kilojoules. So we will stop here and we'll continue with more electrochemistry in the next video.